So, a lot of people that are tube curious end up buying one of these 6J1 preamplifier kits just to see what the hype is all about. The problem is they put it together and then they hook it up and basically it sounds like a toy. So in today's video, I'm going to show you how to take one of these 6J1 tube amplifier kits and actually turn it into a piece of hi-fi. I'm excited. I've worked on this for a while, and I am really impressed with the results. It isn't hi-fi aficionado quality, but it's pretty good for what it is. So when you get your amp kit, you're just going to build it so that you have this section done, which is basically the top section on the amplifier of both tubes. So it's just this section for both tubes. And this is what it's going to look like. All the power supply stuff is going to be gone. You don't need it. You're also going to need one of these. It's a buck converter that'll go up to 60 volts. If you look it up on eBay, you can see it's a 400 watt DC to DC step up boost buck voltage converter capable of 15 amps. Usually they sell for around 11 or 12 bucks and then whatever it is in shipping. But if we look at the specs on this thing, input voltage DC 8 volts to 50 volts, output is 10 to 60 volts. Max output current's 12. You'll never even get close to that. So, and here's the voltage adjustments, CV and CC. So you'll have to adjust the voltage to 56 volts, and the current you adjust it up so that you can get your amplifier to work. I thought I had found the holy grail to this 6J1 amp. We pulled out the dirty power supply and we added a DC to DC step-up buck converter here. Running off my power supply, the results of the audio output were pretty good. It's pretty quiet. That's with the volume all the way up. You can see the input is 12.6 volts, and it was set there because of the filament voltage. We're pulling about 248 milliamps at about 3.1 watts. So all those specs are good. I'm running through a cheap RCA stereo amplifier that was bought at Radio Shack a long time ago. It's not the greatest for audio output, but for our purposes, it does its job rather well. So then I got to thinking, and I was like, most people are going to use one of these as a power supply. So I tried this one. And this is a cheaper one. I tried this one. And I also added a voltage regulator. This is an LM317 voltage regulator. And you can see the cap is different. And that's because I plugged in the wrong type of power supply. You can't really see it on here, but we'll add this one. Some of these power supplies, on this particular one, the positive goes to the center conductor and the negative goes to the outer shield. Some power supplies have that opposite. So if you accidentally plug in a power supply that is opposite to that, and you reverse polarize a cap, it goes off like a firecracker. Luckily, I didn't damage any other part of the voltage regulator, so I could still use it. So I went ahead and plugged in the bigger one, and it's not bad, but as we turn the amp up, you hear it? There's the noise. So this is the supply we just had installed. It's a 1000 milliamps, it's 12 volts, actually puts out about 16, so that's why you need the voltage regulator. It's probably got some big capacitors in here to do the filtration. but you still heard the hum. Now, there are going to be people out there that use the cheaper version. This is 12 volts, 1 amp, but you can hear that that is horrible. That is your power supply noise. And if they use this type of power supply with this amp, they're going to have that at high volume. So I went on the web and found out that this is just a basic design for a capacitor multiplier. So I'm wondering what's going to happen if we take this and put this in line with the circuit. Can we get rid of the hum from a regular wall wart power supply? I went to my stash and I didn't have any tip 120s, but I do have tip 102s. So I'm going to take a tip 102 and then connect it to a 2.2K resistor and put a 100 microfarad cap on the base of it. And I'm going to put this diode in here for reverse protection so that if somebody hooks a wall power supply in that is of the wrong polarity, the diode will fry rather than eating up the transistor. And we're going to lay it out on this scrap piece of copper PCB material just to see if it works. So I realize this is rather crude, but we're just prototyping here. So I'm going to go ahead and drill the holes, and then we'll scratch out where we don't want connections on the back. We'll put this thing together and we'll see how well it performs. So we've drawn out the circuit schematic that we need on the back. So we'll go ahead and scratch out those lines and we'll put it together. So it looks rather crude, but we've cut all the lines with a Dremel tool and then checked it out with a multimeter to make sure that none of them are shorted together with the exception of the ground. Well, I'll be damned, guys. That worked. That, at least on the big supply, it cut down the noise amazingly. So we have the capacitive multiplier going into the voltage regulator, and the voltage regulator is just there to protect the filaments and keep them at 12.6 volts so we don't burn out the heater elements. At 12.6 volts, is going into this buck converter, which is making 56 volts, which is tied into the board. I'll go into that in a few minutes. But I can turn the volume all the way up, and we'll put you down here. You hear anything? If there's anything there, it's very little. Okay, this is the noisy supply. And you can hear it already. It helped, but that noisy supply is just that, a noisy supply. So at this point, I decided there was too many variables with wall-mounted power supplies. So I'm going to give you the power supply that works so that everybody has the same experience and they get high fidelity rather than noise. So basically on this supply, we have a fuse, and I would say I would put that at half an amp, because you saw from the power supply that it draws about 250 milliamps, so you're covered. So if you have a 12 volt transformer, you can just pull this out of a box or anywhere, but as long as the 12 volt transformer has 500 milliamps, you're good. You run that into a full wave bridge rectifier, which you can make from 1N4001s, 1N4000, mine's 1N4007s, because they handle higher voltage. But, you know, any bridge rectifier that can handle 500 milliamps will work on this supply. I have two 1000 microfarad caps at 50 volts each. So they are your primary filtration from the diode bridge rectifier. I left this diode in there. I don't know if it's necessary or not. It's a 1N4007. and it just would pass any, if something were to happen over here that would allow negative voltage through, it would just drop that to ground. So here's our tip 102, our capacitor multiplier. So we have the tip 102, we have a 2.2 K ohm resistor, it's a 1/2 watt. It is tied to the base. The collector is tied here, and the emitter is tied over here. Then off the base, we have a 100 microfarad, and I just used a 50 volt cap because it's the same as these out here. So then that comes out here, goes into a 100 microfarad 35 volt cap. Because the most this transformer puts out is 16 volts, so you're covered there. That goes into a 7812 voltage regulator. And the interesting thing about this voltage regulator is if you put a diode on the ground connection to the 7812, rather than 12 volts, it's going to give you 12.6 volts. So we have a 4007 here diode, or 4007 diode, 1N4007 diode here that drops 0.6 volts and brings the voltage up here to 12.6 volts. So on the output of the regulator, we have a 470 microfarad cap at 35 volts. So that's the final filtration. And your power connections are as such. You have your rectified filtered voltage coming from your transformer, your rectifier, and your caps coming in here. Your regulated and filtered output voltage coming from here goes into the buck converter, and then a pair splits off to the 6J1 amplifier. Your positive goes here, your negative goes here. Then on the output of the buck converter, your 56 volts is on the orange wire right here, and your ground is on the white wire. So let's get you down closer. The positive goes to C4 on the positive side. The negative goes to, I believe that's C8 on the negative side, and it has to go there on the top of the board because you have a run that goes from the top of the board over to here, comes over to here, and then goes down underneath. So you absolutely need the ground hooked up here, the positive hooked up here, the 56 volts. So right here we're hooked to the input of the diode, which would be right here on the schematic. So this is what we got coming in. So what we're seeing on the scope is about a 744 millivolt peak to peak, 120 hertz filtered noise going into the capacitor multiplier. So we've moved our probe to this point right here, and we observed that our cyclic RMS voltage went down to 2 millivolts. We've got some random noise on there, and it's coming from a lot of it's coming from the fluorescent light. So if I turn that off, it goes down. But peak to peak, without the fluorescent light on, we have it only about 44 millivolts, and it's, you know, a higher frequency. You're not going to hear it. So we've moved to the output of the 12.6 volt regulator. And we can see our outputs, a DC line. We can see a little bit of noise, not a whole lot. But it's sitting at 12.4 volts on the scope, which is perfectly okay for the filament heaters. So now we're looking at the output of the buck converter. And you'll notice the frequency is hanging around 14.2 megahertz. The average human can only hear up to 20 kilohertz, so the noise that you see on the output of the buck converter, you're never going to hear that. So here we have a 1000 hertz sine wave at 51 millivolts, 51.7, coming in across a 10K resistor. And the output's on a 10K resistor, and we can see that we have 320 millivolts of cyclic RMS, about 978 or 970, 968, 970 peak to peak. And that's our 1000 hertz. So if we have 50 millivolts in and 320 millivolts out, and this is just across one tube, and the output is across a 10K resistor also for like a preamp input. But we got about a gain of 6.4. Now, if we turn our input voltage up, right there, you can see the rounding off, and that is the wonderful tube distortion that audiophiles seem to like. I don't get it, but that's tube distortion. There's no hard clipping. So we're going to take a look at frequency response. This is what we're looking at. 640 millivolts at cyclic RMS at 1000 hertz. So we're going to go up to 20 kilohertz. So at 20 kilohertz, you can see we still have 620 millivolts of cyclic RMS, and we didn't lose anything. So the frequency response going up to 20 kilohertz is pretty consistent. So this is 30 hertz. So you see we've dropped off some. We haven't quite dropped off 3 dB. We're going to go down to 20. There's 20 hertz. We got about a 3 dB drop off estimating the sine wave. And then 10 hertz, we totally drop off. So the frequency response is pretty good from about 30 up to 20 kilohertz. I've got the volume all the way up and you don't hear anything. So we're going to go to, we'll see if we get a copyright strike on this, but we're going to go to YouTube. It says absolutely free music, so I'm going to use this for a demo. We'll go ahead and hit play. to show you that we're coming out of the preamp. And the music ends. So to go back and recap, this is just like I said, a cheap audio amp. I bet it would sound a lot better out of a good amp, but if you were too curious, you can actually make a pretty quiet preamp out of this thing. So there you have it. We took a kind of a play toy kit, turned it into a piece of hi-fi. If you enjoyed this video, please like and subscribe, and we'll see you on the next one.